Hello and welcome. It turns out the previous goodness of fit test that we saw, the chi-squared goodness of fit test, was for discrete distributions. What do you do if the distribution is continuous? Quite often we try to fit gamma distribution, we try to fit exponential, we try to fit normal distribution. How do you know if the fit is good or not? It turns out for normal distributions there are very strong tests of normality. There are so many other tests of normality that you can have, but nevertheless chi-squared test is also one possible test. Okay. So, basic idea when you do continuous distribution goodness of fit is to convert continuous to discrete by doing binning. Okay. So, instead of thinking of the distribution as being continuous, I will pick intervals and count only when whether the sample fell into the interval. So, I convert to discrete. Okay. So, to be very precise, supposing you have x distributed according to fx of x and x is continuous with PDF fx of x. Okay. So, let us say that's what's going on. It's continuous with PDF fx of x and you have n samples. Okay. So, what I do is I first define bins. There is a bin A0 to A1. So, if you want a better visualization, you could think of the axis where x is taking values, and this will all be A0 here, A1 here, A2 here, so on. Okay. And you have AK minus 1. The first bin is here, the second bin is here, the last bin is here, etc. So, you have n samples, some of them will fall into this bin, some of them will fall into this bin, some of them will fall into this bin. Okay. You just count how many samples fall into each bin. Okay. So, the bin probabilities, the probability that x falls within that interval, I can calculate. I know the PDF of x. What's the probability that x is between ai minus 1 and ai? I will call that pi. And that I can find, given the PDF I can find. I integrate from ai minus 1 to ai fx of x dx. So, this pi is known, this is known given to me, given that I have this x. Okay. So, I can find the observed counts yk is number of samples in the bin ak minus 1 ak. Likewise, y1 is the number of samples in the bin a0 a1, and I can also find the expected count. Okay, NP1, NP2, NPK. So, notice how continuous became discrete, right. So, I bin the intervals, I picked some intervals. So, it is almost as if I converted my continuous to a less precise discrete random variable. Okay. So, once I do that, I have the count. So, there is this rule of thumb that you pick bins so that each yi will be at least 5. It's a rule of thumb. So, this is always true in any histogramming. You should pick bins so that you at least have a few samples in every bin, otherwise it will look really bad and it's not a good idea. And you want the sum of the probabilities to be 1, you want it to be fully covered. If it's not covered, then it's not a good idea. You fully cover the whole area. In fact, typically you may choose A0 to be very, very large and negative, AK to be very, very large and positive, so that you get the whole thing, maybe even infinity, whatever, so that it works out properly. Okay. So, once you do this, you have this table, and once you have this table, its chi-squared test is obvious, right. So, it's very easy to do this. Test is same as before. So, you just go to a test statistic, which is y1 minus np1 squared by np1 plus so on, and degree of freedom is k minus 1. Okay. So, that is the idea. So, same as before. What do I mean by same as before? I equals 1 to k yi minus npi squared by npi, and degree of freedom equals k minus 1. That is it. So, you can do this quite easily. I've shown a quick illustration of this for the beta 3,3 distribution, and you can do this for any other case also. Beta distribution is between 0 and 1. Okay. So, I'm creating 5 bins here, 0, 0, 0.2, 0.2, 0.4, 0.4, 0.6, 0.6, 0.8, 0.81. Maybe you can close some interval, open some interval if you're very particular. There are 100 samples, and in my observation I got 7, 23, 40, 28, 6. The expected value is 5.8. How do I compute it? So I've shown here expected count for 0.2, 0.4 is 100 times the CDF. So, this is the CDF of beta 3,3, and the CDF evaluated at 0.4 minus CDF evaluated at 0.2. So, this is probability that beta 3,3 falls in the interval 0.2, 0.4. Okay. So, I multiply that by 100, I get my expected count 25.9. That is how I got the expected count here. That is why I got the observed count was given to me. Now, I am ready to do chi-squared test. I evaluate my t, it is 1.09, and I might do a p-value instead of doing significance level and all that. A p-value is 0.895, it's quite high, and you can accept the fit to beta 33. So this is a good fit to beta 33. Okay, some statistical analysis, and these kind of methods are solid, and once people accept it, it's very much useful to agree on fits. Okay, so hopefully that gave you an idea of how to use chi-squared tests for continuous distribution. In the next little module, we'll see how chi-squared test can be used for testing independence. Okay, so quite often you have observations which you put down in a table like this. Here's a cross-tabulation. Let's say there are students who have grades in 3 different subjects, 3 different courses, Math 1, Stats 1 and CT, right. So 3 different subject names, and there are 7 grades, and at the end of a term we went and tallied and looked at this, right. So how many people got S in Math 1, how many people got A in Math 1, like that, and there were 800 students in Math 1. Okay, so this is number of students in Math 1. Okay, like that, and this is a number of students who got S in total number of students who got S in at least one of these courses, right. So in one subject at least. Oh, this is not number of, I'm sorry, this is not number of students. Number of students is not correct here. Number of S grades awarded. Okay, that term. Okay, so that's the way to think of it. So the total adds both ways to 4,800. There's lots of names for this. Some people call this contingency table. I like cross-tabulation. Any one of these names is good enough. So you have these numbers. Okay, and you may want to ask, whenever you have a table, a cross-tabulation like this, are the 2 things independent, right? So are the grades independent of subjects? Okay, so it's a very reasonable thing to ask. So what is the randomness here? There are these, the 4,800 student course combinations. Okay, and you can pick a random student and find out whether they were in Math 1, whether they were in Stats 1, whether they were in Stats 2, and what grade they got in that subject. And are these 2 things going to be independent? That's the sort of question that we are asking. It's interesting to ask these kind of questions at the end of a term, right? We can find out if people perform, the performance was independent of the course or it dependent on the course. So some very useful result to have, I think. Okay, but these numbers are cooked up, by the way. This is not real at all. I've just cooked this up. You'll see the result at the end. You may not believe the result, but I've cooked up these numbers. Okay. So one can do marginal PMF calculations, right? So supposing you want to do marginal PMF for the grades, you will get probability of S to be 90 by 4,800, probability of A to be 582 by 4,800, etc. Okay, so for the marginal distribution of the grades, I'm using just this case. These guys get used in this. Okay, so likewise, I can also do marginal distribution for the subjects. Okay, so this gets used here. Okay, so 800 by 4,800 will be the probability that I find someone who took Math 1, 4,500 by 4,800, etc. Okay, so that's the sort of ratio that one can expect. Okay, so if it were to be independent, if the grades were independent, what should be the count of Math 1 comma S? How many people are expected to get Math 1 comma S? The probability there I have to multiply, right? So I can take 800 by 4,800 multiplied by 90 by 4,800, right? So this is the probability. This is sort of like Pij, and this is n. This is number of such samples that I've taken. So I'll get n times Pij. So Pij is like probability of I times probability of j, I think. So I'm multiplying those two. I is Math 1, j is S, like that. So think of it as a 2-dimensional, right? Two indices are there. So 800 by 4,800 times 90 by 4,800 times 4,800, you get 15. Okay, so this is the sort of what you expect if the 2 things were independent, the subjects and the grades were independent. So likewise, you can do for Stats 1 comma A, it will be 1,500 by 4,800 times 582 by 4,800 times 4,800. You can see why the probability has to be multiplied by number of such samples. to get the actual result, it's 181.9, etc. So you can get actual observed counts of the grades and expected count if the distributions were to be independent. Okay. Once you have observed versus expected, you can run a classic chi-squared test. Okay. So that's what we will do for testing for independence also. Okay. So you have observed, which was given to you. You have expected if independent, which we computed in the manner that I described. Okay. Hopefully this is clear to you. It's slightly involved. Pay attention to how I took the ratios and how we multiplied. It's sort of like, row total times column total divided by overall total. Okay, so that's one way to remember this. So for instance, if you were to look at this number, this would be row total, if you are the one who likes formulae better than how they came from, divided by grand total. Okay, so that would be the row total for C is 2321, column total for C is 2321, row total for stats 1 is 1500, grand total is 4800. If you did this, you will get 725.3. So that's how these numbers are obtained. You can do observed versus expected if independent in this fashion. Once you have observed versus expected, you can do a chi-square test. Okay. So how does the chi-square test go? This is the general test. I have also shown you the example. The null hypothesis is the joint PMF is product of the marginals. The alternative hypothesis is it is not. Okay. What is my test statistic? I am going to sum up over all ij, all the two coordinates, yij, which is the observed, minus npij, which is expected, squared divided by npij. Same as the chi-squared test statistic. It's a product of marginals for ij is pij and npij is expected if they are independent. If you do this calculation for the previous example, you end up getting 0.012 for the test statistic. It's close to 0, right? So you expect the fit to be good in some sense. Here's an approximation for t. So this guy ends up being chi-squared with a DOF, and this DOF is number of rows minus 1 times number of columns minus 1. Right? Previously, when we had k different possibilities for the random variable, the degree of freedom was very easy, just k minus 1. In this case, given the constraints and how that linear algebra works in the approximation, I said there's some linear algebra in the approximation. How it works is the actual degrees of freedom is number of rows minus 1 times the number of columns minus 1. Okay, so the approximate distribution of t in the example that we had is going to be chi-squared with 3 minus 1 times 7 minus 1. So that's 2 times 6, which is 12 degrees of freedom. So this is one minor change when you go to this two-dimensional distribution type thing, because there are constraints for every row and there's a constraint for every column. The sum of the rows should be something, some of the columns should be something. So overall, there'll be this minus 1 multiplying. Okay. So once you do that, the test is, remainder of the test is very easy. If you reject H naught, you can reject H naught if t is greater than something, right? We expect t to be small. It's greater than some critical value, you reject H naught, and significance level is 1 minus, in this case, CDF of chi-squared, right? So this guy is CDF of chi-squared 12, okay? Because degree of freedom is 12, evaluated at the critical value. If you like p-value, you can do 1 minus f chi-squared 12 of 0.012, and that's 0.999, shows very good fit, right? High p-value, you accept the null hypothesis, okay? So if you were to believe this, if you were to believe this data, you would say the grades are independent of the courses, whether it's Math 1, Stats 1 or CT. Probably you don't believe that, so clearly this is cooked up data. Maybe we can look at the actual data in a particular term and see how well the chi-square test predicts something. Okay, so that's the end of this lecture. Thank you very much.